Good afternoon, everyone. Welcome to the second talk of this session, Finding Spammers and Scammers Through Rate Tracking with Python and Redis with Mica Swyers and Jay Chan. Before we get started, I have one quick note. We're trying to get everyone to complete surveys on the closed captioning during today. Those are up on the front corner of the stage, and please come fill one out after the talk is over. And with that, I will hand it off to you guys.
Yeah. This one? Is my mic on? Yes. Okay, great. Hi, everyone. I'm Mica Swyers.
I'm Jay Chan.
And hopefully you've come here to learn about finding spammers and scammers with rate tracking, through rate tracking with Python and Redis. Before we begin, I have a little bit of audience interaction that I would like to request. So can I get everyone to stand up in their seats, please? For real, stand up. Great. Okay. Can I have everyone put their hand over their heart? Or some area in your chest. Okay. And then take a step to your left. Okay, so now, no matter what Jay and I say, you can leave this talk knowing that you have seen a talk that is uplifting, heartwarming, and moving. And now you can sit down. Jay loves presenting with me. Okay, so let's go ahead and get started.
All right, so we'll give a quick overview of our talk. We're going to start with a background of who we are, what rate tracking is, and why you need it. Then we'll give an introduction to Redis itself, and then a detailed description of our implementation of a smart rate tracker that we call the Velocity Engine. Then we'll give some odds and ends about that particular implementation, and then we'll close with some questions. Yeah.
Great. So we have two main objectives for our talk today. We want you to leave this session with the answers to two questions. The first is, what is rate tracking? Hopefully you've come to this talk because you want to learn about rate tracking or learn more about it. And then second, how can I build a smarter implementation of a rate tracker using Python and Redis? There are some limitations of naive rate tracking that we're going to go over, and then we're going to talk about an implementation of a rate tracker that we built that will overcome some of those limitations. So we'll start with some background about ourselves and about rate tracking in general. So Jay and I work on the site integrity team at Eventbrite. This should be obvious because we exude so much personal integrity up here on the stage, but more importantly, what that means is that we are charged with preserving the integrity of Eventbrite as a site. This means building tools that help prevent spammers, scammers, fraudsters, and other users with nefarious intentions from degrading the integrity of Eventbrite as a site. It's a pretty small team. This is the 4 of us, and for an abbreviated version, this is the 4 of us with our faces morphed together into one. So, rate tracking, what is it? Rate tracking basically answers the question, how fast is someone doing something? You may remember from grade school physical science that a rate is simply distance over time. In this case, rate that we're referring to here is the number of actions of interest divided over the a given period of time. So this could be something like, say, logins or page views or clicks over a given period of time, an hour bucket or a 10-minute bucket. Yeah, okay.
So why do we need rate tracking? So for example, at the site integrity team at Eventbrite, we deal with bad people who are trying to take advantage of us, right? So for example, spammers tend to do things at an increased velocity. So rate tracking and limiting the rate is very important to us. We also block even harder attacks, such as distributed denial of service attacks or DDoSing, which is just overloading the site so that no one else can use it. Also at Eventbrite, we use it for good purposes too. So we can track popular events by tracking the rate of clicks on an event or page views and so forth. So the simple or naive or traditional implementation of a rate tracker would go something like this, would be for a particular hour, count how many actions are happening in that hour. But it does have some limitations. So at the end of that hour, your count resets. So at the beginning of the next hour, it seems like your rate is at 0 and the count is nothing, right? So that's an issue. There's also no way to track changes in your rates. So throughout that hour, what is the rates? There's also a lack of granularity. So once your rate tracker is running, let's say, counting the actions per hour, there's no way of re-asking the question, what is the number of actions per 15 minutes? So after all that, let's give a short introduction to Redis itself.
Great. So when the site integrity team sat down and tried to figure out how we were going to build this smart implementation of a rate tracker to overcome some of those limitations, we knew we needed a backend data store that would have very fast reads and very fast writes. So Jay floated the idea of using Redis. I was unfamiliar with Redis when we started. Raise your hand if you are familiar with Redis, if you've used it before. Okay, cool. So this may be a review for some of you. Just to go over it quickly, Redis is an open source in-memory key value data store. That is a mouthful that I took off the website, but basically that means that it has very fast reads and very fast writes. It would be pretty crappy if we built a rate tracker about tracking rates that was slow and sad. But when we were talking about just having an in-memory data store, I thought, well, why don't we just use some other like fart of memory in RAM? Why don't we use memcache or something? But the cool thing about Redis is that it supports structured and other abstract data types, one of which I'm going to talk about right now on the next slide. So Redis supports the Redis hash. I like to think of this as a dictionary mapping strings to other strings. And just a note about terminology, in a Redis hash, what you would think of as the key of the dictionary is called the field, and this maps to a value, so field and values.
Right, but no data store is perfect. So Redis is bound, it's all in memory, so it's bound by the amount of RAM you have. And so there's an option to write your data to disk also, but it does slow down performance. But it's okay because the way we store our velocity data is very easily shardable, so it's horizontally scalable. So how do we talk to Redis? So there's a library called Redis Pie. It's really awesome because all Redis commands are mapped to Python functions. So it feels like you're talking directly to Redis itself. And then to deal with the problem of keeping your data in memory, we shard our data over multiple Redis nodes in a Redis cluster. So we have a custom sharding client that abstracts away the Redis cluster so it looks like we're talking to one node. So let's give a detailed explanation of our implementation of the rate tracker that we're calling the velocity engine.
Okay, so obviously the name Velocity Engine, velocity being a synonym with rate, it's a pretty badass name, so it should have some badass features to back that up. So first of all, we can emulate windowing. Remember that Jay said one of the limitations of a naive or traditional rate tracker is at the end of every bucket, your counts are going to reset. So at the start of the next window, all of your counts have reset to 0 and your rate data looks artificially low. So with the Velocity Engine, what we were able to do was have a time window that slides along the timeline so that our counts never reset and look artificially low. We can also emulate arbitrary granularity. You're not just set with the original time buckets that you set in your settings file. We can actually add together multiple windows, say down to 1 second, up to an hour or more. We can add those together to get different arbitrary looks at our data. And then finally, we were able to track the top in actors. By top in actors, we mean the actors with the highest rates. So say a user with the most login attempts or an event page that has the most clicks on it in a given period of time. So in Redis, we have a schema. I'm putting that in quotes there. What I mean is this is what our Redis data structure looks like. So remember I said that we're using Redis as a dictionary full of dictionaries. So the key of that outer dictionary is a string with 2 pieces of information in it. The first is the action of interest that we're trying to count. For this presentation, we'll talk about logins as our example action. This is a string concatenated with the granularity. We're just using this to refer to the length of that bucket of time or window in which we're looking at that action. So those are together to make the outer key. And this maps to the Redis hash, which I like to think of as the inner dictionary. The field, or again, the key of the Redis hash is a variable we refer to as divided time. This is simply a Unix timestamp divided by the granularity. So some timestamp divided by, say, 10 seconds. We'll use 10 seconds as our example granularity in this talk. And then this field maps to the value count, and count is simply the number of times that that action has occurred in a given time period.
So let's give a short digression on divided time itself. We used the divided time to group actions together, okay? So for example, we have here a timeline from 78 seconds to 94 seconds. Let's say that there are two actions happening at 81 seconds and 87 seconds, and we wanted to group these two together in the same window of granularity. And if we wanted to group them in the same 10 seconds, we can divide 81 and 87, and both of those will result in 8. So we can use 8 as the field of our inner dictionary, and the resulting Redis structure looks something like this. We have our action of login per 10 seconds of granularity, pointing to the inner hash with 8 as the field, and the two grouped actions 2 as the count.
Great, so in our settings file, we need to set up in advance what information or what actions we want to track, and then how we actually want to look at it. So this is a dictionary mapping a string representing the action to a list of tuples. Each tuple contains two pieces of information. The first is that granularity, or the length of the window that we're looking at. So we'll say 10 seconds in this example. And then it also has the number of those buckets that we want to keep. So let's say in this example, we're looking at the login action, and we're tracking it in 3 different ways. The first is 12 10-second buckets. 12 times 10 is 120, or 120 seconds. That is 2 minutes broken down into 10-second increments. We're also looking at 10 1-minute buckets, so the last 10 minutes broken down into 1 minute increments. And then finally, we're looking at the last 10 hours broken up into 1 hour increments. So before we get into a deeper dive into the code, let's just walk through an example of how the velocity engine works. So we've simplified that last slide that we just looked at. We are just looking at the login action as the example, and we're only looking at it in one window here. We are looking at the last 12 10-second buckets, the last 2 minutes broken down into 10-second increments. Now, how do we actually increment those counts and track that rate data? We make 3 separate calls to the increment velocity function, we'll say for this example, with 3 pieces of information. We first take an argument representing the action that we're actually tracking, so the login. We also want to look at pass in the count, or that represents the number of times that action has occurred, so 1, 3, and 5 respectively. And then we also need to pass in the now parameter. This is simply a Unix timestamp representing when that action occurred. Just a note, for simplicity, we are using low timestamps, so we can all pretend that this is a throwback to, say, the first few minutes of 1970. Okay, so we've stored all that data in Redis. We need to get it back out because it's basically useless to store data if you don't do anything with it. So we make a call to the lookup velocity function. We want to give it which action we're actually tracking, so again, the login. And then we also need to pass in the timestamp for when we are looking up that information. We pass in that now parameter because we want to have a point of time reference from which we can look back in time and look at the rate data. Now, this will return a dictionary mapping a granularity, or in this case 10 seconds, to a list of values. Let's go over that list of values. The first item in it is 0. You can see that this would be a 0 count. This represents the 10-second period in which you're making the lookup velocity call. So from timestamp 100 to 109. As you can see, we didn't make up any call to the increment velocity function during that time period, so we would expect our count to be 0. If we move to the second item in the list, you can see the count is 5. That obviously corresponds to the increment velocity function function we made with a count of 5 at timestamp 92. And then the third item in the list is a count of 4. That's from adding together the 2 increment velocity calls that we made between timestamps 80 and 89. So you can see that in this list of values, it's broken up into 12 10-second counts. However, we could also add the first 3 values together and see a different view of the data. We can see that there were 9 total login actions over the last 30 seconds. Again, we're emulating sort of an arbitrary granularity in this case.
So let's talk about how we actually increment velocity in terms of code. So here we have the increment velocity function. It takes 3 parameters: the action we're dealing with, the count of the number of actions happening, and at what time it's happening at. The first thing we do is we loop over the pre-configured granularity and number of buckets, and we create the key and we create the divided time. And we use the Redis client and call the hinker-by function, which is hash increment by. This takes 3 parameters: the key, the divided time, and the count, and it creates that structure we've been talking about. Afterwards, we do a Redis client.expire, and we expire this with the granularity times the number of buckets. So in our example, it was 10 seconds and 12 of those, so it'd be 120 seconds or 2 minutes. And we expire after 2 minutes because after 2 minutes, all your counts drop off the end of the number of buckets, so it's not useful anyway, so let's just expire the key. You also notice that we've looped over our number of granularities and did an h increment by and an expire. And when we do that, it's a lot of calls to Redis over the network, and there is some performance problems there. So what we can do is leverage the Redis pipeline. And what pipelining does is it groups all of your calls together and makes one network call. And this is a really good performance improvement. So here is the code once again, but this time we're using a pipeline. We do a Redis.pipeline, and we create a pipeline object. And once again, we loop over our granularities. We create the key and divided time. And this time, instead of calling hinker-by from the Redis client, we actually do it from the pipeline. So pipeline.hash increment by and pipeline.expire. And at the very end, we call pipeline.execute, and it pushes all of those commands to Redis at one time. So that's great. We have our data inside our Redis. Now let's get it back out. So here's our lookup velocity function. It takes 2 parameters, action and now. One small digression on the now parameter, we explicitly break this out instead of calling time.time inside the function. And doing this makes your code much easier to test. You can mock out all your velocity calls much easier, and you can pretend that you're at different points in time. So once again, we open a pipeline and we loop over our granularities. This time we call pipeline.hgetAll or hash get all for the key that we want. And once we execute the pipeline, we get back a list of those dictionaries that we had. And here is now the 8 in the field and 4 in the count.
Great. So the second part of the lookup velocity function is translating that values list that was returned from the hgetAll, or as I like to call it, the hgetAll. In Redis. Jay's so uncomfortable right now. Okay, so we're going from this data structure that you see up on the screen to the one that I went over in the example, which is the dictionary mapping the granularity, in this case 10 seconds, to the list of values. We find this to be a preferred format to look at the data because instead of it just being kind of hidden in the dictionary, you can actually see the history of the rates over time, which makes it a little bit easier to see the change of rates over time as well. The code that translates one structure from the other is actually pretty cool Python code. It is a bit involved and outside of the scope of this talk. So because we're all Pythonistas, we're going to leave that as an exercise to you, the audience. Okay, so now we're going to go over some odds and ends just about our specific implementation of smarter rate tracking, which again we're calling the velocity engine. So remember that in the increment code, we set the expiration to be out in time, say the number of buckets times the granularity. In our example, that would be 120 seconds in the future. You can see how this would be problematic, however. Let's say that someone created some sort of bot that was trying to log in once a second all day. That key for logins will never get a chance to expire because every time we're incrementing that login, the key expiration date will be set farther and farther in the future. So that hash will grow much too large and definitely larger than the amount of data that we need. We call this a hot hash. I think hot hash is pretty gross. Corned beef hash is really gross. So by extension, hot Redis hashes would also be kind of gross. So how are we going to clean those up? We built a housekeeper job that looks in Redis, loops over all of the keys, and checks the length of the hashes. If any of those hashes are longer than we need, say past that granularity times number of buckets setting, then we just trim them down to a manageable size. This keeps our data in Redis, this keeps our data in Redis, making up words. It keeps it manageable and tidy and keeps things running efficiently.
So we also mentioned that we can emulate different granularities. So the way we're storing data in Redis now makes it very easy to write functions to mix and match the different granularities we already have to get the granularities we want. So let's say we wanted now to ask the question, how many actions were there in the last 1.5 hours? All we have to do is add up the last hour with 3 10-minute buckets before that, and granularities is now very easy. Another note about our actions is that actions are actually faceted. What we mean by that is it's not enough to track the rate of your actions happening site-wide. We actually care about who is doing those actions on the site. So for example, here we're tracking the IP address 8888. I don't know why they're hitting our site, but we want that for the logins. So here is the action, here is the type of facet we're tracking, in this case IP address, the actual value of the IP address, and the granularity 10 seconds. So in our other example of tracking popular events, we can also do the same thing of answering what is our most popular event. And here, page views is our action, and this is to the event 1, 2, 3, 4, 5 over the last 60 seconds. One last thing is that we can also track the top-end actors. Unfortunately, it's out of the scope of this talk. It's a little bit involved. So I urge you to read our blog post. We actually call our top-end actors heavy hitters, and this is a good read. But we actually use heavy hitters pretty frequently in the site integrity team. We can answer stuff like, who is our most egregious spammer? And all we have to do is track who is sending the most messages. We can also answer questions like, who is our most valuable customer? And then we would just track ticket sales per buyer.
Great, so the TLDPA version of our talk looks like this. First of all, rate tracking is pretty cool. If you were unfamiliar with it before entering the talk, hopefully now you have an idea of what rate tracking can add or what rate tracking can do for you. It gives you a pretty interesting look at your data. It can help us, like on the Eventbrite site integrity team, find users with malicious intentions. That being said, naive rate tracking does have some limitations, namely that the counts reset, there's no way to look at change of rates over time, you're stuck with those granularities that you set at the beginning. So how would you deal with those limitations? Well, you need to track things intelligently. So you want to be able to actually not have your counts reset and never have artificially low data. You want to be able to have a more fine-grained look at your rate data, say down to the second, and to be able to add up all of those windows together to get more a finely tuned view of your data. And how would you track things intelligently? Well, we think that the velocity engine is pretty cool, and we built it using Python and Redis. Okay, so with that being said, are there any questions? Okay, and you should also read that blog post.
So, question?
Yeah. This was a great talk, but there's a question I still have, which is how do you differentiate something being popular to a DDoS?
We did mention this, but the way we actually track things feeds into another system which aggregates all of these velocities, also like reputation of users and other things, and then it goes into a machine learning system, and then at the end it gives us a score, and then we say, oh, that score is bad, so go away.
Are you able to differentiate an active user from a click farm?
Yes.
Okay.
And it's stuff like have we seen them before? We look for like IP ranges. We look for if you're coming from data center. That's a good signal. I mean, there's a ton of stuff we look at, and yes, we are able to.
Is everything open source?
No.
No, not yet. Maybe.
Okay.
But we're glad you're interested.
Thank you.
Wait, actually, the answer to that is I hope our talk was enlightening enough so that you can implement it yourself.
And if you have questions, you can contact us. Jay's not on Twitter, but he has a blog.
Any other
also
questions?
have T-shirts if anyone wants to ask questions and get one. And as a side note, I totally wanted to call this talk 8 Fast, 8 Furious, Velocity Engine, but that was shot down. I was very disappointed.
So I'll ask a quick question around the black box yellow arrow you drew that sort of left as the exercise, and the trade-offs of have you evaluated time series databases that have built-in windowing so that you're essentially, I guess, are there times you wish you still had? I guess you have all the raw data, but is that yellow line ever a performance problem for you if it's doing a lot of the aggregation in Python?
So two-part answer. The yellow part, no, it's not a problem. All it actually does is we calculate the divided time of now, and then we walk back and do the hgetalls, and calculate it that way. The second answer on why we used Redis in the first place was to implement the heavy hitters, we actually use some Redis Lua code. And it's just really cool. You just have to read the blog. That's all I have to say.
Fair enough. Thanks.
Yes.
I was wondering how you guys were dealing with long-term data. So you were saying that you have expiry dates in Redis, and does the data from Redis get dumped anywhere so you can do long-term data analysis? Or how do you guys handle that?
Okay, yeah, so we do not. All of this is more for like real time, like, hey, something's happening on our site right now, let's stop it, or something good's happening on the site, let's encourage it, right? For the more important stuff like buyers and important like page views and all that stuff, we actually have other mechanisms like aggregate it through Kafka and Hive and all that stuff. So this is just for really quick decisions on the fly on the front end.
Right, I got you. Thanks.
Well, that's a question. Yes.
You said you had some cleanup code that actually goes and looks through like all the keys and like purges the ones that are having a problem.
Yep.
I recall there being like big warning flags in the Redis documentation that particular operation is really slow and you should absolutely not use it in production. I'm wondering how you're coping with that.
There's two ways actually we looked at dealing with this. In Redis 2.6, well, actually, first of all, in Redis 2.8, there's a function called scan, which you call scan once, it returns you some set of keys and then a cursor, which is just an integer, and then you call it the cursor and it gives you another set of random keys, quote unquote random, and you can keep doing that over and over, and it's actually really fast. And you can actually, by doing that, look through all your keys and trim them that way. If you're on Redis 2.6, there's a function called, it's like random keys or something like that. I don't remember the actual name, but that what you can do is just say, okay, give me 1,000 random keys, 10,000 random keys, clean it up, and then in the next minute, clean up the next 10 random keys. And all you have to do is just call that over and over and over.
Okay.
Any more questions?
Oh, okay.
So right now, IP chicken shows that I'm 66.171.172.34 because I'm inside this network. Do you have another way of tracking besides IP? We've implemented things before, but like a school or someplace, they all come from the same IP. It causes kind of a false, record of logins or whatever.
Yes.
We don't want to share.
Somewhat proprietary.
Okay.
We do.
Stuff like cookies. I mean, you can clean it up, but like cookies is one thing you can look at.
So you do
but
have ways
proprietary
to track
stuff.
it other than
Huh?
Okay. You do have ways other than IP.
We
Yes.
do have ways.
Maybe.
No.
You guys mentioned the importance of seeing like the rate changes, and I can see how you can actually deduce it from this. But I'm wondering, like, what kind of, like, how are you using it? Are you just like plotting it out, or do you have some kind of like automatic triggers that for which this rate change is important?
Yes, we actually compare big jumps in rates. So there's algorithms out there, papers and whatever, saying, okay, this rate changed above a certain deviation, stop it. And it actually helps that we also keep track of the top end actions. With that, we also keep the count of those top end actions too, and all of that aggregated together lets you say, okay, this is definitely a weird signal. There's a weird spike, so do something with it.
And that can be added to our business logic and also to catch spammers and fraudsters.
Okay, thanks again, you guys. Just a reminder, there's the surveys up there on the front corner of the stage. If you could please complete one for us, it'd be great. Otherwise, thanks for coming by and have a great afternoon.
Come up if you want shirts.
Shirts.